Let's take a look at the application of the derivatives. The gradient of a function can be seen as the rate at which a function changes. And we say this change could either be a positive change or a positive rate of change, which indicates that the function is increasing, or a negative rate of change, which indicates that the function is decreasing. So let's take a look at these examples over here. The first one says the temperature inside a jet engine in degrees Celsius after t seconds is. A says determine the rate of increase after 7 seconds. So the rate would then be the derivative of z. That's going to give us 12 e to the power of 2 minus 144 plus 500. We forgot a t here. And we're then going to substitute in the t is equals to 7 seconds. Which will then give us 80 degrees Celsius a second. So we can see that it was increasing by 80 degrees Celsius per second at t is equals to 7 seconds. Then B says determine t where the rate of increase is at its maximum. And this is when it is now changing from the concave up to the concave down. So it's going to be that our point of inflation. This is now where the second derivative is equals to 0. So the second derivative would be 24t minus 144. And we have to solve where this is equals to 0. So we'll have 24t is equals to 144. Divide both sides by 24, and we'll get that t is equals to 6. We can also use our derivative to optimize or to minimize. Let's take a look at this question here. It says that the area of a rectangle ABCD sketched below is 2,400 meters squared, and they tell us that DC is in X meters. It then says we need to determine AD in terms of X. So what we do know is that we understand that the area of the rectangle is given by length times breadth. And here our AD is our length and our breadth is DC. Okay, so we want to rewrite AD as and make it the subject of formula. We get that AD is equals to the area over DC. So we will get 2,400 over X, and that is expressing AD with regards to X. 1.2, it says that if the rectangle is fence and the fence EF divides the triangle in half, find the length X so that the total length of the fencing is minimized. Okay, so that means we're only working with ED at this moment, right? So then ED would be half of AD, so we get 3,400 to X. That gives us 1,200 over X. And we want it so that what do we want to minimize? the length of the fencing is minimized, right? So then how do we get the length of the fencing? We get the length of the fencing by getting the parameter, right? So in terms of what we have, I do believe we will be only fencing this side. Let's just see if the rectangle is fenced and the fence EF divides the rectangle in half. Find the length of X so that the total length of the fencing is minimized. So that's going to be our parameter. So perimeter here would be 2 times the breadth plus 2 times into d, so width. So that's 1,200 x, and you can divide that as 2x plus 2,400 x to the power of minus 1. To minimize it, we will look for the derivative, which is going to be 2 minus 2,400 and x to the power of minus 2. We know that the fence will be a minimum when we have x is equals to 0. So here we would have 2,400 x minus 2, let's write it as 2, x over 2 is equals to 2, multiply both sides by x, multiply both sides by x squared, then we'll get 2x squared is equals to 2,000. We'll divide both sides, we get that x is 1,200, and we'll square root both sides. Square root will give us 20 square root of 3, or we will get 34.6 meters. So they were only asked us to find x, and then we did. Sometimes they will ask you what is the length. That means that now you need to take your x and substitute it back into your parameter equation and find what that parameter will be. But yes, this is then the minimum of x with all the restrictions we are given.